Hello and welcome to this Electrical Principles training video. It's my absolute privilege to be featuring on the E5 Group channel in this video, and I'm stood here with Mr. Paul Meenan, the main man who is trying to currently improve the electrical industry for the better along with E5. So thank you so much for having me on your channel, Paul.
Thanks for having us, Joe.
Much appreciated. It's a real pleasure. So in this video, what we're going to be doing is we're going to be considering the effect of DC currents on AC RCDs. Now this is something that's becoming a little bit more of a problem as time goes on. Why is that, Paul?
It is. The electrical installations in modern times are engaging with more and more technology, more products that are manipulating wave and current forms. And the technology we have been using for the last 10 or 15 years is becoming obsolete to an extent. And we have various challenges where we need to enhance our knowledge of how the new equipment that we're using within installations can affect the electrical safety and performance of our electrical installations.
Very good. So what we're going to see, we're going to go over to some footage that we shot earlier with our learners. We're going to see what happens when DC current leaks into an AC circuit and the effect that has on an RCD. And then we're going to come back here and we're going to explain with the aid of a drawing and with the aid of some software just exactly what's going on with these RCDs. So cut to the footage.
Let's give you a quick example of where DC can affect an RCD within a domestic installation. Everybody's worked in a domestic fuse board in some way or another. You've gone in, you've put a supply to Mrs. Jones's shed. 6 months later, you've been called back. Her husband's been given an electric shock, and you think to yourself, what have I done? Well, you know, I'm going to have to go back and check this. Now, any electrician who works on electrical installation obviously will test the RCD because obviously he's running a supply outside. When he tests the RCD, very simply, he sets it to half times I delta N, pushes his test button, and it shouldn't trip because obviously it's not required to, which is great. It does that on both sides of the sine wave. For speed, I'm not going to. It then does it at I delta N, so it's a 30 milliamp rated RCD, and he does it again because when he's testing, that's exactly what he should do, and it trips out. Now it should trip within 300 milliseconds in accordance with product standard BSEN 61008 or 009. And he's great. He's thinking, you know, it works on the I delta N. I'm then going to do the super mega test of somebody cutting straight through a cable. Let's go for 5 times I delta N. Go through, and that should trip within 40 milliseconds in accordance with the standard. 25 milliseconds. Jobs are good 'un. Now, the one recommendation I always say to Sparks, before you leave a new installation, do a ramp test. You want to know how sensitive that RCD is, because the last thing you want to do is the next day you've got a 3-day job booked and you're being called back. So I always recommend you do a ramp test to see how sensitive the device that the wholesalers have provided. And this one, 25 milliamps. I have occasionally found devices that have been 16, 17, 18, and with time and wear, these will also change the characteristics of the device. So that's fine. So you've now tested it, you've certified it, jobs are good 'un. 6 months later, husband's received a shock. You've got to go back and you're thinking, well, what have I done wrong? First thing you do is you get your tester out and say, well, the RCD works, not a problem at all. So again, you'll do your RCD test. You obviously make sure power's on. You go half times and it won't trip. And you think, yeah, fine, there's no problem here. You'll go to 1 time. And what you'll also do then, you'll do 1 time and you'll make sure it trips because jobs are good and it should trip out within 300 milliseconds. Oh no, there you go, it's not tripped out. What's happened there? Well, what I've actually done is I've just injected 250 milliamps of DC current. Now I don't know that because I've just done my 1 times test. So I'm thinking, well, it's a mystery. How do I solve the mystery? I know what I'll do. There's a problem with the RCD. I'll push the trip button. That's what I'll do. So I'll push the trip button. No, it's not working. Bugger. So okay, so the trip button does not work. It's saturated with DC. So I've got a problem. So I'll tell you what I'll do. I'll do a ramp test to see if I can unseize it. Maybe there's something I'm not aware of. I'll do a ramp test and I'll see what comes of the ramp test, because the ramp test is a great feature. At this time we know there's a problem. I'm doing a ramp test. Oh no, and it's come back greater than 33 milliamps. So it's not tripping. It's gone past the rating of the RCD. I know what I'll do. I'll switch up the rating. I'll tell you what, I'll be a bit dangerous. I'll go to 300 milliamps and let's see where we go. So it should trip in a minute or so. Oh, there we go. It does trip. Great. 195 milliamps. So there's enough there to kill somebody at some point. So we've got a major problem. So naturally, what do? We go out, you'll go into the van, you'll sit and you'll scratch your head and you'll go, have I done something wrong? And then what you'll do is you'll look up and you'll go, solar panels on the roof. Oh, that's what that box was next to the mains. There's an inverter there. Well, let's go in and have a quick look. Open up the box of the inverter, maybe burnt out DC terminals coming in. There may be damage where the DC enters the box because it's not been protected against mechanical damage. Or it may be that someone's run a bond up to the metallic framework of the PV array and there's a damaged cell which is naturally producing DC and leaking down into the earthing system, which naturally, obviously, earth and neutral are combined in some form as it leaves the installation. However, DC does what it wants and goes where it wants. It doesn't perform or behave the same way AC does. So we need to be aware of that. And this is why you guys are being taught about the hazards of AC type RCDs. When they came out, they were fine. They were fit for purpose. We had resistive loads everywhere in our houses. Now we have low energy, we have electronic loads. So those protection characteristics can cause effectively unseen hazards that we need to be now considering. Now, if you walk into a house and it's across the road from a railway station and it's a third railway, and there's no PV, then there's probably something being picked up onto the supply cable from the railway. But more than likely, it's probably going to be an EV or a PV, or even something as silly as a USB socket outlet where you fitted it onto a 25mm back box. It's got the rectifier is cheap quality, it's got hot and melted, but sufficient just for DC to leak out the back of the rectifier, because these things don't switch off. I found that once. So henceforth, my first video wasn't going to be about USBs, but it ended up being about USBs and sockets. So there you go. So this is a real serious problem. It does not trip. It saturates that magnetic core. It interferes with that sine wave. So the easiest way I've ever explained it, and I actually did this in my chartership interview, was I said to the chap interviewing me, I said, I've done a lot of research on how DC affects RCDs. He went, well, how does that work? To explain how an RCD works. So I said to him, well, I'll give you the detailed version and the simple version. And he said, okay, I'll have the simple version. So I said, look, I'm an RCD and I'm looking for a fault. So Gary, you're a fault. When you call my name, then I'll react as an RCD would. Okay, so I'm looking for a fault. Gary, call my name. Paul? Yes. Straight away I've reacted, and that device would then react and trip and cut the supply. I'm now an RCD that's saturated with DC. Please call my name.
Paul. Paul. Paul.
Sorry, did you call me?
No.
Eventually, they can trip. If you do a 5 times I delta N, it's very hit and miss as to whether they actually trip, depending on the magnitude of the fault current. But it's a real eye-opener. So if you do have that, this is why I suggest you go through that sequence of test, check the button. A perfect example of this was I worked on Docklands Light Railway, third railway traction system. During the day, I could walk up to an RCD, I can push the button, and it did nothing. But when we did the electrical inspection and testing, when would you do that on a railway?
Yeah, when it's closed down.
When it's closed and there's no traction power. So when it's closed and there's no traction power, guess what? Passes the functional test. Great. Operational interruptions can give false readings, and this is the problem. I've got certificates handed to me where they've said it's great, I've gone out there, pushed the button and gone, no it's not my contractor's fault, it's the operational restrictions of the EICR that I'm doing. But it's well worth noting, I always say to guys, if there's 2 regulations you learn, 13216, your alterations additions, bonding, imperative for safety, but also Appendix 5, external influences. I work on a railway that goes parallel with the sea. So if you come onto my railway and you select and erect some conduit and trunking, it's either going to be GRP or stainless, because when you look into the detail of external influences, it will actually describe salt mist testing and pollution categories, which as Sparks we don't get involved with. But when you start looking at working from the regulations, you'll find your knowledge will immediately start opening up, and what you'll find is you'll actually provide a far better quality product for your clients. So it's just something to be aware of.
So we just saw some really, really worrying effects of what happens when you apply DC current into an AC RCD, Paul, and we discussed how potentially that could be happening inside typical domestic, commercial, industrial installations. I'd say that if you weren't worried by what you just saw in that piece of video, you didn't really understand the implications of what we were looking at there. Some pretty serious effects there, Paul.
Indeed, and for the video you've just watched as well, for speed, we didn't test on both sides of the sine wave, because on both sides of the sine wave when we tested it, it comes out the same result. So it was just for speed that we just measured it on one side of the sine wave, just for speed and gravity of the guys watching. But the effects are still the same on both sides of the sine wave.
Really important point there. So what we're going to do now is we're just going to try and explain some of the science behind what's happening inside that RCD. To understand this fully, we need to understand how a healthy RCD operates. So here we've got a very simplified drawing of the internal workings of an AC type RCD. And what we've got is inside the RCD, we've got this iron core, which is easily magnetized, which is really important.
Yeah.
We've got the line conductor passing through, and that's wrapped around the iron core. Sometimes it goes straight through the middle, but the principle is exactly the same.
Yeah.
And then the return path of the neutral is behaving in the same way. And then wrapped around this side of the iron core, we've got a small loop here, again, inside an actual RCD. This might be looped around many times, but we've just simplified it here. And that's what communicates with the little tripping device inside the RCBO or the RCD, which is going to disconnect the circuit under fault conditions, we hope.
Indeed.
So when it's healthy, when the circuit's happy, current flows down the line through that coil and then back into the circuit, goes into the circuit to the load, and then the current flows back down the neutral again through the coil in the RCD and back out again. Now, we know, Paul, when current flows through a coil, what is generated around the coil?
Electromagnetic field.
An electromagnetic field. Now, in this case, because the electromagnetic field in the line and the neutral are going to be acting in opposition to each other, because the current's travelling in opposite directions, whichever part of the cycle we're on, the magnetic fields are kind of balanced, if you like. They have no effect. They appear within the iron core, but they do not create any kind of current inside this little coil here. So under healthy conditions, there's no current being generated inside this little coil, and therefore the tripping unit is quite happy. Would you agree with that, Paul?
Yeah, I agree with that.
That's good. It's nice to know I'm explaining it right so far. That's good.
No,
Paul's just confirming what I'm saying.
No, absolutely. And if you're wondering, because you probably will be wondering, if I push the circuit for tripping, what that does is that pushes that to a position where it induces enough a current onto that coil where it does cause the device to disconnect.
Really good point. Okay, so that's great. Now, when a healthy AC circuit develops an earth fault, some of the current that's flowing down the line disappears off down a different path, down the earth path, either through a person, literal earth, or down a CPC and out to the earth that way.
Yeah.
Now, when that happens, generally speaking, we will have more current flowing in the line conductor than we will have flowing in the neutral, because some of this current flowing back is going somewhere else. Therefore, the strength of the magnetic field generated around this coil is weaker than the magnetic field generated around this coil. And because this one's slightly stronger, Paul, what effect does that have on this little coil here?
It effectively, excuse me, it effectively causes an imbalance on that coil.
Yeah, absolutely. Because we've got a stronger magnetic field coming from this coil, it creates a little bit of current inside that coil, which then triggers the tripping circuit if it's of sufficient difference. So if more than 30 milliamps is disappearing down the CPC from the line or down through a person to earth, then that will generate sufficient current inside the coil to trip this out.
Absolutely,
and the circuit
tells
trips.
it to trip.
Fantastic.
Yep.
Now the problem occurs when we start to have DC current being injected back into this AC circuit by some kind of load that we've got connected up to that. And what would be typical loads that would generate that DC flowing back into the AC circuit?
Within a domestic installation, a faulty EV charger, inverter, a direct PV leak of DC. It could be a variable speed drive on a domestic washing machine that's faulty. It could be EV, PV or inverter driven devices is probably more than likely. You may get a faulty phone charger which could accidentally earth out and cause some leakage. USB sockets potentially.
Fantastic. So again, you work primarily in the sort of industrial industry on the rail line.
Heavy rail, overhead line, DC.
And we see that problem happening there, which is obviously a bit of a concern.
Yeah.
But what's even more of a concern is that we're seeing this happening in domestic properties, places where people who are not skilled, who don't have training, probably don't test their RCD as often as they should, are very much susceptible to this kind of thing happening. This is not something that's happening remotely, it's something that's happening in people's homes.
Yes.
So it is a real concern. Now, to understand how this DC electricity is affecting our AC type RCD, we need to understand a little bit about what happens when we put DC current into an AC supply. So what we're going to do is we're going to nip over to our graphing software, and we're going to see what happens when we put DC into an AC circuit. So what actually happens when DC current starts to get added into an AC circuit? Well, we can illustrate it on the board here. What we've got here, and don't worry too much about the numbers over on the left, these are just kind of random numbers that we've chosen to illustrate a point here. You can see the red waveform is a healthy AC waveform. Now the important point is that on the positive cycle it's peaking at 10, and on the negative cycle it's peaking at the same value. Yep. Now a smooth DC waveform, as generated by some of the things that Paul mentioned earlier, looks something like this. So there's our DC waveform. So that looks quite comfy, that sits quite happily there. It's just, in theory, a straight line. Okay. Now obviously we do get other types of DC.
We do indeed. So that straight line could be directly from a leaking battery, a UPS, a PV system that's generating a smooth DC output. Stuff like TVs, washing machines, they use switch mode power supplies, rectifiers, which chop the DC. But for this example, it's just constant, smooth DC current.
Now what I'm going to do here is I'm very simply going to look at what happens if we bring that DC waveform back down to 0. So we'll get that down to 0 there. And then what I'm going to do is I'm actually going to tell the software just to add those two waveforms together. So what we're doing here now is every time I increase the size of the DC waveform, we're going to see the effect of what happens when we add that into the sine wave. And essentially when we inject DC into an AC system, this is what happens to the supply. So if I start now adding DC current into this supply, watch what happens to the AC waveform. Can you see that it starts to rise up and up and up? Now that's an interesting effect there, because what we're actually seeing here is the fact that we've still got an AC waveform, but can you see how on the positive part of the cycle, the current goes to a much higher value, and then on the negative part of the cycle, it's not quite as strong as it was. Now don't get this mixed up by thinking this represents what's flowing down the line and what's flowing down the neutral. We're simply changing the direction of the current flow, and that is key to understanding what's happening inside our RCD. So you can see there very clearly, the more current that we add into our AC waveform, the more and more we end up with a higher value on the positive part of the cycle. Then when the current changes direction in the negative part of the cycle, the current is actually lower. So what we'll do now is we'll nip back over to the board and we'll have a little bit of a look at why that then affects the RCD. So Paul, we've just seen on the computer screen the effect there of what happens when we add DC into an AC current. We end up with the positive part of the cycle having a much higher current than the negative part of the cycle. Yeah. Now the reason this becomes a problem is it has an effect on the iron core. This is actually the bit that kind of causes us the problem, because the iron core can become shocked, stunned or saturated by that higher current in the positive direction. Now the reason that happens is that inside this iron core, the little molecules of iron are all shaped like little tiny bar magnets. So they all sort of look a bit like this. Now when current is applied in the positive part of the cycle, the molecules all flip to follow the path of that magnetism that is applied to it. And then when the current changes direction, they flip back the other way again. They're kind of constantly changing their polarity in line with the changing of polarity of the current flow. Now, the problem arises because we've injected DC back into this circuit, the positive part of the cycle becomes a higher current. And the effect of that is that all of the molecules inside this core become lined up with each other in one direction. But then when the current changes direction into that smaller negative part of the cycle, there is not enough magnetism generated to flip those back round the other way completely. And because of that, the iron core remains slightly magnetized.
It does.
It's that expression again, being saturated, which is when a magnetic core all the molecules end up lined up in one way. Okay, the technical term for what's happening here is remanence. So if I use the word remanence, I just mean leftover magnetism in the core. So then what we're looking at is as the current is flowing, we end up with this iron core remaining slightly magnetized. And then if a fault occurs, because this iron core is still slightly magnetised, there is not enough magnetism generated by the imbalance in the two coils to fight against that remaining magnetic field and generate enough current inside this coil to trip the RCD.
Absolutely.
And that is the big problem. The RCD has to generate a much higher imbalance between the line and the neutral. There has to be a bigger flow of current to earth to generate the tiny amount of current that is required to trip the RCD. Would you agree with that, Paul?
Absolutely. So the devices themselves, if you look at the I delta N of a 30 milliamp RCD, if this device was the basic device for a 30 milliamp I delta N, the number of windings would be proportionate to the current that was needed to trip it. If you are saturating that device, you're effectively stunning or delaying the performance of the balance of the electromagnetic field. Henceforth, it will trip, but you need a huge current. As we saw in the video, we did a ramp test on a 30 milliamp RCD and it took 195 milliamps to take the device out. So what that means is if you have devices which are saturated by DC, not only will the test button not see the shunt coil, but it will also delay and hinder the performance of the device to the British standard that it's made to, which is a problem. It happens a lot in industrial environments, but more domestic now because of the new technology we're bringing in. Hence BS 7671 introduced type A's, type F, type B's. We now have to consider electromagnetics as an external influence in a far more sterner light now.
Absolutely. So hopefully we can see from the information that we've watched in this video that if you have the types of load which are becoming increasingly common that feed DC back into an AC circuit, either under their normal operation or even worse under when they've gone faulty, and then a typical domestic fault occurs where line and neutral or neutral and CPC come into contact with each other, or worse still, somebody gets a shock, then the RCD is not going to trip when just 30 milliamps flows through a person. Now, if we get more than 30 milliamps flowing through a person, that is a serious problem because it goes above the level where someone can die.
And this is fault conditions, guys. Now, a lot of you will be watching thinking, but I have AC type RCDs, are they all dangerous? No, not necessarily. However, what you need to be mindful of is the connected loads within the installation. Because they're microelectronics and power electronics, they can saturate, they can leak, they can perform in a way which we're not used to. Hence, they can perform in a way which can affect connected components of the electrical installation. Now, as this knowledge grows, the knowledge of how we select and erect and the wiring regulations changes to inform us accordingly. Hence this video today.
Absolutely. So I think, Paul, we've covered that material really nicely, both with practical presentations and also with the science behind what's actually happening inside that RCD. So I think you probably don't know how I end my videos because not many people get to the end of my videos. So I normally say thank you very much for watching. So
Thank you very much for watching.
Well, let's do it together.
Oh, okay,
okay.
Go on
So
thank you very much for watching.